Dr. Adila have a bachelor degree from University Tun Hussein on Malaysia in 2009, and then continue her master degree also in UTHM in 2012, and finally he finished her doctorate degree in RMIT University Melbourne, Australia, 2017. Dr. Dila have many experience in wastewater engineering, in not only in design but also in research. And I can see here he have many teaching experience as a lecturer in engineering mathematics, lecturer on design of wastewater engineering, also in fluid mechanics. Okay, maybe without any further delay, I would like to give time to Dr. Adila, maybe 30 until 1 hour. Okay, please, Dr. Adila, the time is yours.
All right, so I will share my slides here. Which one? Okay. All right, so now can you see my slide?
Not yet. Yeah, now. Okay.
All right. Okay, thank you, Madam Miss Moderator. Bismillahirrahmanirrahim. Assalamualaikum and maybe good afternoon, okay, to all of you. Okay, para dosen, mahasiswa dan maybe seluruh hadirin yang berbahagia yang ada di sini lah. And it's a great honor and privilege for me to be here today. Was invited by Universitas Trisakti to speak at this esteemed session organized by Teknik Lingkungan. Is it true?
Yes, environmental engineering. Yeah.
Oh, yeah. Okay, so I would like to express my sincere gratitude to UTHM as well and your university for this opportunity to share my knowledge and maybe insights with you all. And this is part of the MOU program between our two institutions, which signifies a significant step towards fostering maybe the academic collaboration and maybe some cultural exchange. And I believe that such partnerships are crucial in advancing knowledge in various fields. And today, as a topic stated in the poster, okay, so I'll be discussing on the electrocoagulation in wastewater treatment, and it is more like to fundamental aspect lah, not to more research in depth, right? Okay, so before we move deeper into the topics, let's have an overview on the electrocoagulation in wastewater treatment area. So EC or electrocoagulation is an innovative electrochemical process which utilized for treating either water or wastewater. Okay, so by removing contaminants through the application of electric current. So this method has gained attention due to its effectiveness and eco-friendliness compared to traditional treatment methods. All right. Okay, so while you know that we have a variety type of wastewater treatment techniques available or existing at our disposal, so many of them actually rely heavily on non-renewable energy sources. Okay, so this dependence leads to increased carbon dioxide emissions, and also eventually it will contribute to climate change. Okay, so given this challenge, researchers, academics, and maybe the potential students, okay, which have
recording in progress,
explore on new technologies, and they are not only cost effective and efficient, but also environmentally friendly. So these technologies aim to treat wastewater from various sources of industries without harming the planet. And so far, there are a number of existing technologies for wastewater treatment that have emerged, including the first one, we have the common one, chemical oxidation, okay, nanofiltration, advanced oxidation, adsorption, and biological oxidation. So some of them are tertiary treatment and some of them are maybe biological treatment, right? Okay, so here the tables illustrate the advantages and also the drawbacks, okay, of various wastewater treatment that existing in our society or in our country now. Okay, so we have the I'm not sure in Indonesia which treatment methods are common. Okay, but these are some of the common method. Either it is from Malaysia or Indonesia or maybe around the world. Okay, so the first one is the advanced oxidation process, or known as AOP. So this process highly effective in degrading organic pollutants. So it is specifically will target on the organic pollutants lah compared to the other contaminants. Okay. However, it consumes significant energy and which lead to high operational costs. Okay, and then the second one, we have the adsorption and nanofiltration. So these two methods is efficiently remove certain pollutants, but they generate secondary waste, which requires further treatment. So before we dispose of, we need to ensure that the quality is up to standard lah. And then for the chemical precipitation, although it is simple and effective for inorganic pollutants, but it uses large quantities of chemicals, which it is should be avoid from our environment lah, and potentially it can generate sludge more. Okay, for the biological treatment, okay, we know that it is kind of environmentally friendly and low cost treatment, but it is a slow process. Okay, so it is less effective for inorganic pollutants such as heavy metals and susceptible to operational disturbance. And then the last one, we have reverse osmosis. Okay, this one is like high-end technology that we have in wastewater treatment plant. Okay, it is highly efficient in removing dissolved salts, okay, and organic matter, but we know that it consumes high energy and has potential for membrane fouling and scaling. Okay, so as we can see here, for each of the method, it has its own strengths and also limitations. And the choice of method depends on the specific characteristic of wastewater that we are going to treat and the desired level of treatment and also the available resources that we have. All right. Okay, moving to the next slide, we have here is the electrochemical methods. Okay, so based on the reasons that I've stated in the previous slide, so this kind or type of method, which is called as electrochemical methods, that have emerged as promising alternative, okay, for wastewater treatment due to their simplicity, low chemical usage, and high efficiency. So these methods utilize electrical energy, okay, to induce chemical reactions that facilitates the removal of pollutants. So let's take a look at this slide. So this table is actually provide concise overview of 4 emerging electrochemical methods. Okay, so the first one, we have the EF, or electroflotation. Okay, so this method works by using electrolysis to generate tiny bubbles. Okay, maybe I can turn on my pointer so that you can see. Okay, so this method generate tiny bubbles. Okay, so these tiny bubbles will bring the contaminants to the surface for further removal. Okay, so we can remove the scum layer at the surface of the tank by skimming lah. Okay, skimming process can remove the scum layer. All right. So EF, okay, electroflotation is particularly effective in removing suspended solids and oils, okay, from wastewater. All right, so the second one, we have the electrokinetic remediation or EKR. So in here, this technique utilizes electrical current as well, okay, to enhance movement of contaminants either in soil or also can be applied in water, okay, and wastewater lah. So this movement can facilitate, okay, the degradation and make it valuable tool for cleaning up contaminated site or water. All right, so for the third one, we have the electrocoagulation. Okay, this is our topic today. So EC is part of the electrochemical methods. So in this method, it combines the electrolysis and coagulation at the same time in the same process, okay, to remove particles and contaminants from the wastewater. So basically, the EC have been tried to many type of industrial wastewater, and they excel at handling a wide range of pollutants. All right, so finally, we have the electrooxidation. Okay, so this method employs electrochemical process to oxidize and break down organic pollutants. So EO is excel at degrade complex organic compound and are difficult to be removed by the conventional methods. Okay, so it is important for us to carefully select the electrodes used in this electrooxidation and the operating condition to achieve the optimal operation. Okay, so therefore we can say that each of these electrochemical treatment methods has its own set of advantages and also limitations. So we need to consider each of what is the suitable treatment for our wastewater. So depending on maybe the strength of wastewater, the contaminants contained in the wastewater itself, and the volume, okay, of the wastewater that we are going to treat. All right, so in particular, EC has gained, EC is electrocoagulation. So EC has gained significant attention due to its reliability and versatility. Okay, unlike other technologies, EC can effectively remove wide range of contaminants, including heavy metals, suspended solid, okay, and organic pollutants. And it also offers the simplicity of operation, where the process is relatively simple and easy to operate, and it requires minimal technical expertise to operate the treatment process. And then we have it offers a cost-effective solution, okay, compared to other advanced wastewater treatment technologies, and the process generate minimal residuals and other byproducts, reducing the need for further disposal. And then the EC system can be easily scaled up or to accommodate varying wastewater volumes and also treatment requirements. And lastly is in terms of energy efficiency, EC can be designed to operate at a low energy consumption level, making it an environmentally friendly option. Okay, so this is like schematic diagram of electrocoagulation. So we have the device we call as a power source, okay, and then we have the electrodes, okay. So the electrodes can be made up from various materials lah, but the common ones are aluminium and electrodes. Aluminium and ions. Okay. Okay, so let's explore the theoretical background of EC itself. So based on the provided historical timeline, we need to bear in mind that the core concept behind the EC itself is the electrolysis. Okay, so this process involves passing an electrical current through an electrolyte solution, causing chemical reaction to occur at the electrodes. Okay? So by the history, this is the electrodes and this is the electrolyte solution, and this is our power supply lah. Okay. So in 1820, okay, it started in 1820, where Michael Faraday introduced the concept of electrolysis, and the process occurs in an electrolyte solution, allowing ion transfer between the electrode. Okay, so in the EC cell itself, the positive ions, okay, positive ion that is from the electrode that is connected to the positive charge of the power supply, okay, will allowing ion transfer will travel towards cathode, okay, and are reduced, and simultaneously negative ions travel toward anodes and are oxidized. So there are chemical reactions happen when the process of EC is operated. Okay, and in 1889, the wastewater was electrolyzed in this procedure by mixing it with seawater. Okay, seawater has good electroconductivity. So the major goal of EC process early stages of development was to produce chlorine for odor reduction and disinfection of sewage effluent. So as a water treatment technology, EC has a long story. Okay, and in London, it was first proposed in the year of 1889 and was used in the sewage treatment plant for about 10 years. All right, so move to 1906. Okay, we have A.E. Dietrich invented and patented the EC technique specifically for treating ship bilge water. And then in 1909, we have the J.T. Harris in the USA received a patent, okay, for using aluminium and iron electrodes in EC for wastewater treatment. So this is our background, okay, why we further explore on the use of EC in water and wastewater treatment. All right, so let's break down the advantages of EC, okay? So the advantages as highlighted here. Okay, so the first one we have that EC utilizes electrical current, okay, to treat wastewater, which can eliminate the need for the harmful chemicals. So this chemical-free approach significantly reduces the risk of introducing potentially dangerous substances to our environment. And then the second one, besides, okay, EC also is highly effective in removing a wide range of pollutants, including inorganic compounds such as heavy metals, okay, organic compounds, bacteria, and also suspended solids. So it has a broad spectrum removal capability, which contributes to significantly improving the overall quality of the treated water. And furthermore, the EC also does not require the use of chemicals or special additives, which can reduce the operational costs. So EC equipment is generally affordable and making it accessible for various applications and settings. All right, so to add, EC can be applied in various settings. So when we design the EC reactor, we can actually manipulate several parameters in order to come up with a good reactor, okay, of the EC. So this can be applied in either drinking water treatment, industrial wastewater treatment, okay, municipal wastewater treatment, and agricultural runoff treatment. All right, so therefore we can conclude that EC offers chemical-free, okay, it is efficient, it is cost-effective, and versatile solution, okay, for treating wastewater. So by harnessing the power of electricity, EC will help to protect our environment and improve water quality. Okay, despite of the advantages that I've explained before, so let's now discuss on the limitation and also the challenges of EC as outlined here. So the first one, we have the EC system require regular maintenance, okay? So we know that when everything in the world will have the pro and cons. So this one is the limitation of EC, okay? However, we can actually overcome this by further explore on things that can improve, okay, the operation of the EC. So the first one, the EC system require regular maintenance to ensure optimal functioning. This includes cleaning and replacing the electrodes, okay? And the electrical current also need to be monitored to maintain it within the appropriate range for effective treatment. Okay, besides, EC generates a dense sludge that require proper management to prevent environmental harm. Okay, and the sludge may contain hazardous contaminants, necessitating for careful disposal. So the sludge that is produced at the end of the treatment process is actually required to be monitored in terms of its quality. Okay, either it is harmful or can dispose of directly to the landfill. Okay, so if it's still contain harmful substances, so we need to further treat the sludge. Okay? All right, so the third one, EC may not be effective in removing all types of contaminants from wastewater or from water or wastewater. Maybe some of the organic compounds may not be effectively coagulated during the treatment process, and it requires additional treatment methods, okay, to complete the removal. And EC may not be suitable for treating high concentration or certain contaminants such as some heavy metals. And I would say that even though it is a very valuable technology that we have here, it is still essential to acknowledge its limitation and challenges. However, with proper maintenance, sludge management, and careful consideration, okay, of the types of pollutant present in the wastewater, we can optimize the process or the effectiveness of the EC. So it is good to know the advantages and also the drawbacks, okay, of this treatment so that we can move towards its improvement. All right, so based on the introduction, okay, just the introduction part. Okay, now let me focus on the objective of this knowledge sharing session. Okay, so basically, I've listed 5 objectives that I want to the audience to able to expect what you will get, okay, at the end of this session. So I will try to explain the working principle of EC. So in here, I will try to make you understand on how the electric current is used to coagulate and the precipitate contaminants in the water. And then the second one, to discuss the EC components and also mechanisms. So this will cover the different parts of EC systems such as electrodes, okay, power supply, and also maybe the arrangement of the electrode itself. And then we have I will present the previous studies which showcasing the EC applications. Okay, so in here I will highlight the findings of previous studies on EC being used to treat different types of wastewater. And then the fourth one, to explore the operational parameters that influence treatment efficiency. So in here, we will discuss on the factors like current density, okay, electrode materials, and treatment time that can affect the effectiveness of EC. And the last one, to review or to discuss future trends in research, challenges, and also opportunities. So in here, we will explore the potential EC for future advancements and address any challenges that may arise in its implementation. All right, so let's take a look at this image, which illustrates the working principle of electrocoagulation, or EC. Okay, so this can be broken down into a few components, such as the generation of electrical current. Okay, so you know that the EC will utilize the direct, electric current, which pass through the water or wastewater. So this current creates ions in the solution, facilitating the breakdown of contaminants. Okay, and then we have the electrocoagulation process, where it is the process of the electrical current causes metal ions to be released from the electrodes. Okay, so the electrodes can be made of iron or aluminium, or maybe from other material as well. Okay, so they are still under research. Okay, but the common one are iron and aluminium. So this metal ion get released from the anode. Okay, so the one that is connected to the positive charge of the power supply, we call it anode, and the other one is cathode. Okay, so the metal will react with the contaminants present in the water or wastewater. And then the role of electrode itself significantly impacts the efficiency of the EC process. So the metal ion that is released from the electrodes will combine with the hydroxide ions, OH, in the water to form metal hydroxide. Okay, as you can see here, MOH. It is actually the metal hydroxide precipitate. Okay, so this we can refer it as a adsorbent. Okay, in this system. So the adsorbent will try to form larger flocks, okay, with the other contaminants. If they are heavy, so they will settle at the bottom, and if they are lighter in weight, so they will float at the surface of the water. All right, so let's now take a look at the key components of EC and the process involved in EC. So we have the electrodes. Okay, so the metal plates is actually typically made of aluminium or iron. Okay, so they will be submerged in the sample or in the solution, and these electrodes acts as the source of metal ions during the EC process. And then we have the current source or the power supply. So it is a device that provides necessary electric current to the electrodes. And then we have the flock formation. Okay, so the metal ions that are released from the electrodes due to applied current will react with the hydroxyl ions, okay, in the water to form metal hydroxide flocks, okay, in the water. And then for the sedimentation or flotation, the foam flocks, okay, which are heavier, will settle to the bottom of the tank, okay. And alternatively, in some cases, the flocks may float to the surface, allowing for easier removal by flotation. So overall, the EC process effectively removes suspended solids, organic matter, and heavy metals from wastewater. And the treated water, which is usually cleaner after the treatment, can be safely discharged or reused. All right, so for the mechanism, okay, and we need to know that the EC unit, okay, the electrocoagulation unit consists of electrolytic cells. So electrolytic cell with a cathode and an anode connected to the power source externally and also immersed in the electrolytic solution as shown in this figure. So when the current is passed through the electrolytic cell, an anode will go for oxidation, and the metal will dissociate into either divalent or trivalent metallic ions. So if you want to know either it is divalent or trivalent, it depends on the type of material used for the electrode. So it will release an equal amount of electrons, and even though the electrodes are composed of the same material, Okay, if you use this one is alum and this another one is still alum, so the dissolution of metal still exclusively happen at anode, not at the cathode. All right. And the number of metallic ions generated depending on the applied current density. Okay, so in the optimization study, we will determine how much current density that is optimal to be applied for specific electrocoagulation. And then the process of reduction of water on the cathode results in the formation of hydrogen gas, okay, and hydroxide ions. So the metal driven into the anode dissociate into a metal ion. And then the metal ion form on the cathode will combine with the hydroxyl group to form metal hydroxide. So here we have the metal hydroxide. Okay, so this can be in various species lah. Okay, either it is monomeric or polymeric or soluble or insoluble. So it depends on the combination. Okay, so the metallic hydroxides are very good adsorbent of pollutants since they have high tendency to make bonds with them and form flocks as they have a large surface area. So in the EC cell itself, okay, various secondary reactions will occur, including the production of hydrogen and also the oxygen gas, okay, at the cathode and anode. So these both gases are essential in elimination of flocks that do not settle due to gravity. So some will be float, okay, to the surface of the water, and they can be skimmed off at the end of the treatment. And also the oxygen produced at the anode forms hydrogen peroxide, okay. It is not stated here, but I just want to add the information to you so that you will know. The hydrogen peroxide, it is good to help the oxidation of either toxic or non-toxic species that is present in the water. Okay, so as you can see here, this is a sludge. So the flocks that is formed and has heavier in terms of its weight, so they will sink to the bottom, and the one that is lighter, they will float, okay, to the surface of water. So it's like a separation process lah for the contaminants, okay, for the EC system. Okay, and here we have the chemical reaction happen at the cathode and anode, right? Okay, so now we move to the previous studies on EC application of various types of wastewater. So this is part of maybe findings, okay, summary of findings from previous study. Okay, so it details the specific electrode use, experimental conditions, and also the removal efficiencies for pollutants in, this one is dairy industry wastewater, yeah. And then we have the textile wastewater and then hospital wastewater. So for instance, the aluminium electrodes were arranged for anode and cathode in treating dairy industry wastewater, and also and also for the hospital wastewater. Okay, basically for this one, they want to treat for the COD. So they only achieve around 57%. Okay, it is a moderate efficiency lah. Okay. However, for the textile wastewater, it is good to use the combination of iron and iron, okay, to remove color, okay, at very high percentage, which is 95, and slightly above the average, okay, COD percentage is about 76. Okay, and also for the CIP removal is achieved around 88%, okay, using the combination aluminium and aluminium electrodes. So as you can see here, when they are treating different types of wastewater, they can produce different efficiency removal. Okay, and they will use different experimental condition. So this is the optimized or the optimal condition for each of the treatment. Okay, so this one they use the same electrodes for both cathode and anode. All right, for this one they are using different material of anode and cathode or anode. Okay, I'm not sure. Okay, this one, okay, they show that it is anode, this is cathode. Okay, so aluminum, ferrum, we have the titanium and also manganese oxide. All right, so in here we can see that it can achieve around 99% to 100% removal of COD, BOD, color, and turbidity. Okay, so it is efficient, okay, for the industrial wastewater. Okay, and then for the tannery wastewater, we have the reduction like slightly average, okay, for the COD removal. Color, it is kind of good, okay, around 75 to 95, and ammonia was also excellent at 80 and 96%. Okay, for municipal wastewater also, they can treat to get removal up to 95 to 99% for TSS and BOD. Okay, so if you can see here, different environmental condition is applied, okay, for each of the type of the wastewater treatment they are treating. Okay, so that's why we need to do optimization study in order to get which condition that is optimal for that type of wastewater and for that strength of wastewater. Okay, all right, so for this one we can see that this is a material of electrode. That is, some of them is the same, okay, same material, and the others are combination of different material. Okay, and also they are treating another different type of wastewater. Okay, land leachate. Okay, where we know that land leachate is contain very high strength, okay, of contaminants, and automobile wastewater or car wash wastewater. Okay, and then paper recycling industry wastewater, paint industry. So these are all the removal efficiencies they can get, okay, based on the optimal condition they set for the EC. Okay, and the rest we can summarize that the removal of the target contaminants are different based on different types of wastewaters with different optimal conditions. Okay, so that's why I want to stress on that if you want to further study on the EC, you need to come up first with the optimal condition. So the things that you need to do is the optimization study. Okay, later on, I will show you what are the factors that influence, okay, the removal efficiency of the EC. Sorry. Right, so many. Sorry, yeah. All right. Okay, so the variation, okay, that we have observed before in experimental conditions is according to the type of wastewater arises from several key factors related to specific characteristics and contaminants present in different waste streams. So here are primary reasons for this variety. We have the nature of contaminants in the wastewater, and then the chemical composition, the electrode material and configuration, and also the operational parameters. Okay, for the nature of the contaminants, we know that the wastewater, okay, different type of wastewater will contain varying pollutants, okay, such as oils, okay. Some textile industries will have the dyes, okay, colored contaminants, and also heavy metals, and also organic matter. So different type of wastewater will have different nature of contaminants. Okay, for the second one, for the chemical composition, we know that part of them are the ionic strength, okay, the conductivity, and also the pH of wastewater can influence, okay, the EC process. So different pollutants will react optimally at specific pH. Okay, so later on during the optimization study also, we need to determine at what pH will contribute to a better removal of targeting contaminants. Okay, and then for the electrode material and configuration, so the choice of electrode materials, okay, whether it is aluminium or iron, or maybe some of them from the stainless steel, or maybe from the titanium, manganese oxide. So they have the influence, okay, towards the efficiency of the EC itself. Okay, and their configuration, which is the distance between the electrode, okay, that we put in our reactor also will play an important role. All right, so different electrodes will produce various coagulants, okay, that interact differently with contaminant. So we need to know what type of material that we want to decide on as our electrode in our EC. Okay. For the operational parameters, we have several parameters that usually been optimized for the optimization study. For example, the current density, okay, the electrolysis time, the temperature, okay, must be tailored to specific type of wastewater, especially for the current density, that must be adjusted on the type of contaminant. Maybe commonly, the higher current densities may be necessary for more concentrated or complex waste streams. Okay, for the electrolysis time, it varies according to the pollutant load, which more time may be needed for wastewaters with higher concentrations of contaminants to achieve desired removal efficiencies. All right. So this slide showcases examples, okay? This is part of my students' final year project, okay? They did on the electrocoagulation on different type of wastewater. So for the first project, they carried out an EC process on the car wash wastewater, okay, using aluminium electrodes, okay? And the second one is for treating the chicken slaughterhouse wastewater, but still using aluminium electrodes. Okay, the reason why I choose aluminium electrodes because before this I've tried for the stainless steel and also the iron, but the aluminium electrode still shows excellent removal compared to the other material of electrodes that I've tried lah. Okay, as you can see here, for the car wash wastewater, this is before EC, and this is the appearance of water after the EC. So it kind of clean, right? Okay, so the process is actually can remove the turbidity, okay, turbidity up to 91%, and suspended solid 82%. So it's kind of excellent for these two contaminants. Okay, but it has a moderate effectiveness in reducing COD because it can only remove up to 65% only. And this is the current density applied for this process, which is 29 ampere per square meter at pH 8. And also it requires optimal efficiency at 70 minutes, okay? Okay, so far, if you want to compare for the chicken slaughterhouse wastewater, so basically the strength of wastewater taken from the chicken slaughterhouse wastewater is actually, you can see that it is stronger, okay? The strength is higher compared to this one, actually, because it contains high COD and BOD. Okay, at the end, we only try to get not very clean water, but it can remove up to 81% of COD, turbidity up to 96%, and also suspended solid up to 96%. Okay, so if you compare the optimal conditions applied for these two EC process, which treating different type of wastewater, they applied the optimal condition at different pH, current density, and electrolysis time. So that's why it is important to carry out the optimization study lah. So we know for this kind of wastewater, so this is the optimal condition. For this kind of wastewater, so this is the optimal condition. Okay, so it is important to do the optimization first. Okay, this is another examples of students projects. Okay, and this one they carried out the EC using the aluminum electrodes on the laundry wastewater. Okay, and the other one is to treat the textile wastewater. All right. So it's we can see that at the end, after the treatment method, the water become clearer lah. Okay, and we can see here it is a suspended particles floating. Okay, at the surface of the water, and the other particles are settled at the bottom of the water. And again, the current density, pH, and electrocoagulation time. Okay, for every different type of wastewater that we were treating are different. Okay, so it depends. And it is proven lah. We need to conduct the optimization study because of different type of wastewater. Okay. All right, so some of the key areas for research that maybe you can explore. First up is the development of standardized design guidelines. Okay, I think this one is quite big, but as we move on further by years, we will have the established maybe the theory or the design concept of the EC itself, so we can move to development of standardized design guideline. Okay, so the idea is here to create some consistent blueprints so that we can know that what to expect in terms of the performance. Okay, and this will make it easier for everyone to optimize their systems and get reliable results. Okay, and next, there's a big push for optimization operational parameters, as I mentioned before, where researchers will try to find the best settings, okay, to cut down on the energy use, okay, while we are using the electrical current, right? And these like current density, flow rates, and treatment times are all getting a close look to see how we can maximize performance without wasting energy. Okay, and then the third one, the innovative electrode materials and configuration. It is one of the challenge that electrodes can be passivated over time. Okay, they can be corroded over time. They can be the dissolution happen can lessen in terms of their weights. Okay, so this means that they can stop working as well at the end of the process. So researchers are now exploring new materials and designs to keep those electrodes effective and lasting longer. Okay, and then the fourth one, we have the efficient sludge treatment and disposal. So since EC generate sludge, okay, so we need to find a better way to handle because it is crucial, okay, to just dispose it directly to the landfill without ensuring whether the sludge is still contain harmful chemicals or not. Okay, so researchers are working on minimizing sludge production and figuring out sustainable disposal options to reduce the environmental impact. Okay, also combining with other technologies also could be a game changer. So by exploring how EC can work alongside with other treatment methods, we can take advantage of each method strengths, especially for tackling tricky wastewater. Okay, maybe some wastewater contain complex contaminants. So we need to look forward how the combination between the EC and also other treatment technologies can improve the management or the removal of certain contaminants. Okay. And lastly, there's a focus on addressing the secondary effects of added reagents. Okay, sometimes the chemicals we use can create unwanted byproducts or can cause issues down the line. And researchers also are looking into ways to develop selective removal techniques that target specific contaminants without causing additional problems. Okay, so basically these are another key focus areas for the research which related to the studies on EC. All right, so if we want to know that in which treatment unit of a wastewater treatment plant can electrocoagulation be used as an alternative method of treatment? So basically, here are some common application. Okay, we can refer the electrocoagulation as an alternative method for the primary treatment, as it good in removal of suspended solid. Okay, and also it can be an alternative in secondary treatment because it is good in removal organic material, and also for the tertiary treatment because they can remove heavy metals and also nutrients. Okay, so they can be in several applications, okay, in our existing treatment plant. All right, so this is what I want to explain to you. Okay, just now I said I want to explain to you about the factors that affecting the EC efficiency. Okay, maybe there are still more factors that could affect the EC efficiency, but I could only listed some of them. Okay, this is the common factors that is usually affect the EC efficiency. Okay, so the first one, the spacing, okay, between the electrodes, and then the effect of electrode materials, okay, and then effect of initial pH of the wastewater that we are going to treat, and then the electrolysis time, okay, how long the wastewater sitting in the reactor, and then the current density and energy consumption, temperature, mixing speed, and electrode arrangement. So by carefully controlling these factors, it is possible to optimize, okay, the EC process for efficient and effective wastewater treatment. Okay, now let's take a look in detail, okay. The first factor, which is the spacing between electrodes. So by maintaining an optimal spacing between electrodes will allow for maximum removal efficiency. So we need to get the spacing just right between the electrodes to ensure that the current flows evenly and that we can form flux and then we can form flux effectively. So when the distance is appropriate, it allows for efficient electrolysis, which means that we can get a good release of metal ions and end up with a those helpful metal hydroxide flux, or known as adsorbent lah in our system. Okay, so what if the electrodes are too close together? So it is a tendency that we run the risk of a short circuit. Okay, so this can mess up the current flow and hinder the electrolysis process, which ultimately means we won't remove pollutants as efficiently. On the flip side, if the electrodes are too far apart, then the electric field strength might not be strong enough to get the electrolysis going. So either way, we end up by lower removal efficiency, which is definitely not what we want. And previous studies have suggested that a range of 2 to 5 cm as a suitable distance between the electrodes. However, I would say that it still depends on the size of the reactor, the wastewater strength to be treated, and many other factors actually, yeah. But this one is actually suggested from many previous study lah. Okay, the second factors is the effect of electrode materials. Okay, so we know that the common material of electrode used are from the iron and also aluminium, and others can be from the stainless steel, okay, carbon-based electrodes, and bimetallic electrodes. All right, so I would say that the electrode material significantly impacts the performance of the EC because of the release of the ions, okay, into the solution. If we use the iron electrodes, then the metal release is the iron, okay, iron plus, 2 plus ions in the solution. And then it will react with the hydroxide ion, okay, to form the metal hydroxide flux. Okay, but for the aluminium, it will release the aluminium 3 plus ions, okay, which at the end will form the flux of metal hydroxide, okay, and it is highly effective for removing a wide range of pollutants, okay, but it is more expensive lah than the iron electrodes. Yes, sorry, it's not finished yet. Okay, the third factor is the initial pH of the wastewater or any solution lah. If you want to treat the water itself or the surface water is okay. So the initial pH of the water is also plays an important role in affecting the EC efficiency. So generally a pH range of 6 to 8 is considered optimal for EC. And within this range, the conditions are just right for metal hydroxides to form effectively, which helps with the coagulation process and also improve the pollutant removal efficiency. So when the pH is low or at acidic condition, the solubility of metal hydroxide will increase. And this means that instead of forming solid flux that can effectively bind with contaminants, more of metal hydroxides stay dissolved in water. So as a result, their effectiveness as coagulant is reduced, leading a poorer treatment outcomes. Okay, so that's why we need to optimize our initial pH to determine, okay, which type of pH is suitable for our EC. Okay, on the flip side, we have the too high pH, okay, alkaline condition. So the formation of metal hydroxide flux can be hindered in this situation. So the condition might not favor the aggregation of the flux, which again results in the lower removal efficiency for the pollutants. So this one is in the case of if too low and if too high. So we need to determine the optimal pH, okay, of the solution lah. All right. So the next one, we have the electrolysis time, okay. How long the solution is in contact with the EC process, okay. So the effectiveness of the pollutant removal is a function of electrolysis time. So with an increase in electrolysis time, usually the efficiency of the pollution removal will increase as well. However, when the optimal electrolysis time has reached, the pollutant removal efficiency remains constant and do not improve as we increase the time. So the dissolution of anode produces metal hydroxide. So when increasing electrolysis duration and constant current density, the number of the generated metal hydroxide rises. So the removal of pollutants will not be effective and does not improve when the time exceeds the optimal time, since sufficient numbers of flocks are available for pollutant removal. So in conclusion, for this factor, okay, for the electrolysis time, the residence or the retention of the solution or the overall operation time is dependent on the containment, which we aim to remove, the targeted efficiency, and mostly based on the cost of the process. Okay, so the longer the time, the higher the cost will be. That's why we need to determine the optimal electrolysis time. Okay, the fifth factor is the current density and the energy consumption. So current density is defined as the current per unit area. It is also define the number of metal ions released from the electrode. Okay, and then an increased current density over optimal current density does not affect the removal effectiveness. Okay, because adequate quantities of metal hydroxides are available for pollutant sedimentation. And energy consumption is a process that is directly related to the current density and also our previous factors, which is the electrolysis time. So the longer electrolysis time and the higher current density applied to the EC, the higher energy consumption will be. Okay, so we need to optimize all those factors lah. Okay, so this is the temperature factor, okay, what it can affect the EC. So at higher temperature, it can accelerate the reaction rates and improve the efficiency of the process. However, for lower temperature, it can slow down the process and reduce the effectiveness of the formation. So generally, the improved EC efficiency by accelerating the reaction rates and enhancing flock formation can be obtained by set the electrocoagulation temperature higher, okay, in a higher temperature lah. Sorry, stop moving. Okay, the seventh factors is the mixing speed. Okay, we have the optimal mixing and the excessive mixing. So the optimal mixing is the proper mixing that can enhance the contact between metal ions and also pollutants, which can lead to improved removal efficiency. However, the excessive mixing can break up flocks and hinder sedimentation. So we need to determine at which mixing speed it is can produce high removal efficiency. Okay, the last factor could be the electrode arrangement. Okay, we can arrange our electrode either in monopolar or bipolar or other configurations. Okay, so let's say I just tried to focus on this. Okay, so we have the monopolar parallel. Okay, so the electrodes are arranged in parallel. Okay, but they still have two different polar, which is the positive and negative, and the other one is MPS is actually a monopolar, which is arranged in series. Okay, and the other one is bipolar parallel. Bipolar means we have two charge, okay, and then they are arranged in parallel. Okay, so far according to the findings, the monopolar configuration design has lower operating costs, while the bipolar and higher bipolar configuration and other configuration may have higher contaminant removal efficiencies. So if you want to select to to your EC to be cost effective, then you can choose to apply the monopolar configuration. However, if the cost is not the problem, so you can choose the bipolar or the other configurations, because these two configurations are more likely to produce high removal efficiencies towards certain pollutants. All right, so I managed to list out some of the leading industries recommend for EC process. So you can see here, it is metal surface treatment wastewater, okay, electronic industrial wastewater treatment, textile, okay, food industry wastewater, oil field reinjection, water treatment and reuse, and so many others. Okay, so basically, some of the industries already applied, okay, the EC in their wastewater treatment, okay, and some of them still contemplating of applying the EC because of the cost, okay. However, the efficiency is undoubtful because they can remove various type of pollutants, okay, from the wastewater. Okay, so these are some potential future potential of EC application. Okay, for the technological advancements, so we are looking at developing more efficient and durable electrode materials, which can boost the EC performance and help to cut down the operating costs. And then the integration with other treatment methods, where we can see that by combining EC with other treatment method can improve, okay, the overall performance. And also we can look at the expanding application, where it is an exciting area of the EC to be applied across the broader range of industries such as mining, okay, oil and gas, and agriculture. And also, finally, as more people recognize the benefits of EC, we are likely to see a boost in its adoption by water and wastewater treatment facilities. Okay, because EC itself has a lot to offer in terms of sustainable water management practices by providing efficient and environmentally friendly treatment solution. Okay, so these are challenges in EC application. Okay, so before this, I have stressed on the maybe advantages, and these are kind of challenges in application of EC. So lack of standardized design, scaling up difficulties. Okay, there will also the electrode passivation, which can reduce the efficiency of the treatment. Okay, some of the cases it will require high energy consumption. Okay, we also need to monitor the form flow characteristic, and also there's still limited research on combined technologies, and also the challenges in managing the secondary effects of reagent use to improve the efficiency of the treatment of EC. Okay, so there's still a big gap in research and combined technologies. So while EC is effective on its own, so we haven't explored much about how it could work with other treatment methods. So this limits the ability to develop new efficient strategies for dealing with complex wastewater. All right, so I think that's it. Thank you for your attention. Yeah, I hope that my presentation will be informative and stimulating. And I look forward to engaging in maybe this fruitful discussion with you. And thanks once again for your warm welcome and hospitality. Okay, thank you. Any questions so far?
Okay. Thank you, Dr. Adila, for the very comprehensive and inspiring presentation, especially on IC, electrocoagulation. I'm sorry, I can open my camera. I don't know, is the problem with my laptop, but we can see here, Dr. Adila already explained the advantage, also a limitation, and the industry that kind of industry that we can apply the electrocoagulation. Also, we learn a lot about the future potential of IC application. I know here in this Zoom meeting there are a lot of lecturer also in wastewater treatment, and also my student, Dr. Adila. There are a lot of students here, especially in environmental engineering, and I know maybe there are a lot of questions about your presentation. And as mentioned earlier by Dr. Adila, this guest lecturer is being held as part of the collaboration between Trisakti, Universitas Trisakti, particularly Environmental Engineering Department, and UTHM Malaysia. The knowledge shared today could potentially involve also in a collaboration research project. So before we proceed with the Q&A session, I would like to invite the head of the Environmental Engineering Department, Ms. Astari, to deliver her remark. Ibu Astari, there you are here. Please.
Ya, ya, Ibu Ari. Okay. My connection is not 1 minute. Okay. Is everyone can seeing me right now? Is everyone?
Yeah.
Okay, because
okay.
my connection is not really good at this moment. Okay. Yeah. Assalamualaikum warahmatullahi wabarakatuh. To the honored our guest lecturer, Dr. Nur Adila, also the faculty member who joined today, the Vice Dean First, Ibu Dr. Diana Irvindiati Hendrawan, also the Secretary of Environmental Engineering Department, Ibu Sarah Apirta STMT, and our moderator today, Ibu Aryani Dwi Astuti PhD, all the lecturers and students and other participants today. Good afternoon, everyone. It is with a great pleasure that I welcome you all to this special lecture held in celebration of the 59th anniversary of Universitas Trisakti. We are honored to host Dr. Nur Adila Abdul Aziz from University Tun Hussein on Malaysia, UTHM, as our distinguished international guest lecturer. Today, we have the opportunity to dive into the significant topic of electrocoagulation in wastewater treatment. This subject is not only timely, but also crucial in advancing our understanding of sustainable wastewater treatment and wastewater management, an area of paramount importance in today's environmental engineering landscape. The collaboration between the Environmental Engineering Department of Universitas Trisakti and UTHM Malaysia is a testament to our commitment to fostering international academic exchange and enhancing the quality of education and research in our field. On behalf of the entire faculty, I would like to extend our deepest appreciation and heartfelt thanks to Dr. Nur Adila Abdul Aziz for sharing her invaluable knowledge and expertise with us today. We are truly grateful for your time and effort in enriching our academic environment and contributing to the success of this event. We look forward to an enriching and insightful questions and answer session today after this, and also may this event inspire all of us to push the boundaries of knowledge and to continue contributing to environmental sustainability. Thank you for your participation, and let us make the most of this opportunity to learn and grow together. Thank you. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Ibu Astari. Okay, now we will continue our session with Q&A. Everyone that have question can directly by turning on the microphone or writing in the chat
Halo,
box.
Ibu Aryani.
Yeah.
May I give some questions to Dr. Adila?
Okay.
Okay,
First,
thank you.
Ibu Sarah, please.
Yeah. Okay. Hello, Dr. Adila. Thank you for the material of the seminar today. It's so interesting. So I have two questions. The first one is, how about the energy requirements for electrocoagulation and how it's compared with other advanced treatment methods? And the second one is, in your opinion, what is the future potential of electrocoagulation in addressing global water scarcity and pollution issues? Thank you.
All right. Okay, thank you for your question, Sarah. Okay, for the first questions regarding the what energy requirement.
Yes.
Okay, so the energy requirements before this, I've read in some articles that it said that average around 1 to 3 kilowatt per hour for ton of wastewater. Okay, so I think that is minimal energy consumption for that kind of efficient treatment lah. Okay, however, they're still depending on the strength of wastewater that they are treating. Okay, so we need to study on the characteristic of the wastewater and the contaminants that we want to treat. Okay. And the other question is regarding what? Sorry, can you repeat? Is it the effects or the impact?
What is in your opinion, what is the future potential of this electrocoagulation research in addressing global water scarcity and pollution issues?
Yeah, actually, for the EC itself, it requires the use of electrical current, okay, to generate or to operate. So, in terms of the global adoption of this EC, basically, the EC right now, even though in developing countries, it is applied in the high-end or the manufacturing industries, okay, which require to remove certain complex contaminants from the wastewater. So EC is actually can offer the good solution for that purpose. However, maybe for a common application, maybe for small industries, okay, small, medium enterprises. So they still maybe require a conventional treatment method. Okay, that's my opinion.
Ya, oke, thank you, Dr. Adila. Ibu
Oke.
Aryani, saya kembalikan. Terima
Okay.
kasih.
Thank you, Ibu Sarah. There are a question in the chat box from Ibu Siti Umi Kalsum from Jambi. My question is, has degradation of micro or nanoplastic ever been accomplished with using electrocoagulation technology? How successful is it? In the chat box, Dr. Adila, there is a question
Okay.
from
So
Ibu Siti.
I saw the question.
Yeah.
So yes, the answer is yes. Okay, because microplastic or nanoplastic is actually kind of particulate matter, okay, that is suspended in the wastewater or water, and they can actually form a larger flock, okay, with the metal hydroxide formed during the EC process, and they can be, if it is lighter, then it can float at the surface of the electrocoagulation at the end of the electrocoagulation. But if they are, and I think that microplastic is lighter particles, right? So they tend to float to the surface of water lah, compared they sink to the bottom of the tank. So basically, EC can be used to separate, okay, the microplastics or nanoplastics that is present in the wastewater.
Okay, thank you, Dr. Adila. We still have time. In the chat box, there are one question also from Arlinidia, Ibu Arlinidia. This is student, or I hope can mention the name and affiliation, because there are a lot of students here, but also lecturer that I can, maybe I didn't know the affiliation. First, from Ibu Arlinidia, I would like to ask a question regarding the EC operation and maintenance and in its application for the electrodes. Should electrodes be changed to new electrode for maintaining optimum performance? If so, how long the electrodes have to be changed?
Okay, so basically for this one, it depends on the type of material of electrode that we applied, we adopted in our EC. Okay, so basically for the aluminium itself, some studies state that it's around 12 to 15 months, okay, before we need to change to a new one. Okay, because the electrodes itself will be going for the passivation. Okay, passivation means that the condition where the electrode itself will reduce in terms of its efficiency to remove pollutants from the wastewater. So it's around 12 to 15 months, okay, for the new electrodes to be changed to the new one.
So there are still need new electrodes.
Yeah, still the need for maintenance.
Maintenance.
For that, because in the limitation also I've said about the requirement for the maintenance, right?
Okay.
Yeah.
Okay. I would like to hear a question from student. Can student maybe can raise hand? Tadi sudah kita belajar ya banyak, khususnya nih di antara between of all the student here, some of them is now attend the wastewater treatment plant design lectures. So I hope there are questions from the student also from PLI, mata kuliah PLI. Okay, we will wait the question from student. Now there are one question from Bapak Rahmat Dardi, this student, or maybe can mention the affiliation, right? I'm Rahmat, an EC practitioner based in Indonesia. Oh, praktisi, from IC praktisi. This Pak Rahmat. We have implemented multiple EC system for large-scale operation, including 20 meter cubic per hour and 40 meter cubic per hour for the electroplating and textile sector. I'm encounter an issue with applied electrocoagulation in all refinery wastewater, which has low BOD per COD ratio and a fairly stable pH 6 until 8. Its implementation can reduce TSS by up to 90% with a discharge of 15 meter cubic per hour, but for COD it's only achieve a reduction of 20 until 30%. I'm wondering if there are restriction on the AC process for lowering COD level in certain types of waste that are actually on non-biodegradable. Maybe Pak Rahmat want to ask directly to Dr. Adila or add some question or
Thank you, Bu.
confirmation. Okay.
Sebelumnya, I'm Rahmat. I'm practice of AC in Indonesia. There is some problem in all refinery process of EC that we know has a low BOD per COD. And for the application, we have achieved up to 90% of TSS, but low in COD. That we know the wastewater contain multiple non-biodegradable parameter, and I want to ask about how much the limitation of the EC for COD degradation in wastewater, especially in low BOD per COD wastewater. Thank you.
Okay, to answering the question, this come from industry, right?
Right.
All right. So it depends on the strength of the wastewater itself. Okay, since you said that the ratio COD BOD is a problem regarding to achieve the higher removal compared to the TSS, is if I'm not mistaken. Okay, so may I know what type of electrode material you use in the process?
We use iron electrode in ST41 material.
Okay, so yeah, according to the studies also, we tend to see that different type of electrode use also can affect the ability or capacity of the removal for COD and BOD. Okay, for example, there are several studies that I've referred. Okay, so we can see that for the aluminium, okay, it only can achieve up to 57%. Okay, however, for the other treatment method that treat the industrial wastewater, it can achieve up to 100% for the BOD and COD. So it is likely to see the material of electrode use and also the condition, okay, the optimal condition that apply in your process. Okay, maybe you need to change several parameters or factors that could affect your result. Okay, so there are so many factors that could affect the removal efficiency of the targeting contaminants. Okay, like you said, you want to further improve the efficiency to remove the BOD and COD. So maybe you need to run some optimization on certain parameters.
For the practice one, we have changed the iron electrode to anode electrodes, aluminum electrodes, I mean, but the result is the lowest of TSS reduction and the lowest of COD reduction, and we have used electrolyte like NaCl too, but there is no progress in COD removal. And we have to increasing the current density. As you know, we not use plate condition, but we use the helical system. If we have read some paper that use helical system has a potential in current density, we have to try to the industry for now. But in all refinery is too low in COD reduction. But for practice in textile and electroplating industry, they give highest removal for COD and color and heavy metal. Now, that's I want to ask to
I
you
would say
is
it depends on the wastewater type of wastewater. Yeah.
That I want to ask to Miss Adila is there is a COD limitation for the EC process, or there is some limitation of the kind of wastewater that this wastewater need EC, this wastewater do not need EC, something like that.
Yes, because if we go back to my slide that mentioned about limitation and the challenges about EC, so it said that some organic compounds, so COD, BOD is considered as organic compounds, okay, may not be effectively coagulated during the EC process. So maybe they require additional treatment methods. So we need to incorporate with the other biological treatment methods in order to improve the COD and BOD removal. Okay, so EC is good for TSS and other physical contaminants, but for the organic compounds, they may need another treatment methods to support the removal, to increase the removal.
Okay,
that's from my understanding lah.
Yeah,
okay?
thank you.
All right, thank you.
Terima kasih, Bu.
Okay, thank you, Pak Rahmat. Maybe also, maybe AC process primarily target suspended solid and colloidal particle, maybe rather than dissolved organic pollutant. Maybe that's one. one reason why is it happen in your reactor. Now there are questions from student. Dr. Adila is from Andrew Yuda. She want from Environmental Engineering Department. She want to know about in the previous study on electrocoagulation in various wastewater, why is the electrode used in the textile industry using ferrum maybe iron and not aluminum, such as industrial, dairy, and hospital water. Maybe Andrew want to know why there are different kind of electrode used in the different industry wastewater. And the second, why is the electrocoagulation still difficult to increase the efficiency percentage of sludge treatment? That's from student. Andrew, thank you for that question. Dr. Adila, please.
Okay, so for the first question, I would say that for the research aspect, so this study is actually want to try on the Fe or the iron combination, not the aluminum. Okay, because it is a research, so they can try on any other materials. So yeah, I don't have the straightforward answer for that, but it is a research, so they can try on many others materials of electrodes. Okay, for the second question, why is electrocoagulation still difficult to increase the efficiency percentage of sludge treatment? Okay, we need to know that the sludge produced at the end of the treatment of EC is actually, the characteristic is denser compared to one produced in the conventional treatment. Okay, so still need, okay, we cannot simply rely on EC itself for the removing of sludge, okay, because we still need filtration after that, okay, in order to properly remove the sludge that is produced at the end of the treatment of the EC. Okay, so is it answered?
Okay, there are more questions. Andrew Yuda, I think it's clear enough, yeah? Okay, we move to another question. It's from Mikaela. Mikaela asks about what safety consideration are associated with the high voltage system used in electrocoagulation, and how are these risks mitigated in the treatment facilities? Thank you very much. Okay, Dr. Adila, this question is from graduate new graduate from our.
Basically, yeah, it depends on the electrode surface area. Okay, so that's why our factor is actually current density. Okay, current density depends on the how much surface area of the electrode applied in the EC itself. So if it is big, so it will require higher energy compared to the smaller one, right? So the thing is, if I already mentioned about the energy required, okay, consumption under working condition is actually average around 1 to 3 kilowatt per hour. Okay, so it's still, even though it's considered not so high, okay, but still it needs expert personnel, okay, to at least operate and know how to handle the energy source requirements lah for the EC. Okay. However, the overall process, the operational process is actually is not complex. Okay. The only things that we need to take in precaution is the risk lah regarding the if it is required a high voltage system. However, in here we can consider that the EC itself is not too high compared to the other maybe treatment processes that which require high energy consumption. Okay, so it is a moderately requirement of skillful person for operating that EC operation, yeah. And the SOP still the same with the other operating and safety health regulation lah, according to your country and as well in Malaysia. So still they have to adapt with all those guidelines. Okay.
Okay. Any question? We still have 5 minutes to Dr. Adila. Any question? Okay. Dr. Adila, it seems there are no more questions. I would like to thank you very much for all your explanation. It's kind of very interesting research, yeah, to have applied the AC process and not only in textile. We also see the opportunity to apply this method, yeah, in textile and even in drinking water. I saw your presentation. Yes, we know in the end of this session. Thank you very much. I would like to say thank you for all the audience for the discussion. Very useful, fruitful. Maybe we can continue this.
Yes.
If any still have any question from Dr. Adila. Dr. Adila already gave the email address.
Okay, maybe I can leave my email again here in the chat.
Yes. Okay. And also on behalf, yeah. Maybe Dr. Adila can show again in share screen the email.
Okay, for the PowerPoint slide, maybe I can share with Miss Aryani later. I will deal with her.
Okay.
Okay.
Thanks again for all the participants and also Dr. Adila. Hopefully this lecture is not the first, but we hope that we can collaborate again in maybe in research project, or maybe there are some students here that interested in this research. We can collaborate with UTHM. Okay.
Yeah, I'm happy to assist you. Thank you.
Thank you. Again, thank you for all the participants. Thank you for Dr. Adila. So I will close this session, this international guest lecture that organized by Environmental Engineering Department, and on behalf Universitas Trisakti. Again, I would like to thank Dr. Adila and also Dr. Aislina that already there are a lot of collaboration. Maybe we can meet next November in Batu Pahat, because I myself with Dr. Ratna Ningsih will join the webinar as speaker in UTHM. Okay, thank you, Dr. Adila. Yes, next week, yeah, in the next week. Okay, thank you for all the participants and have a good day today. Thank you, Doctor.
Thank you too.
Thank you, Dr. Adila.
Okay, welcome.